Okay, so in this set of notes, we're going to talk about atomic structure, and more specifically, we're going to talk about periodic trends. So you did some graphing, and now we're going to look at how does that relate to the whole periodic table. All right, so in this first section, we're going to classify the three main types of elements, and notice that the first type on the left here is the metals. It is the majority of the elements that are found in the periodic table. Notice they are good conductors, and as a result of it, they will transfer heat and electricity. So there's a reason why we have plastic on our charging cords, because if we didn't, we probably would get zapped from the electricity that's coming out of the outlet. Where you see malleable, that means we can essentially flatten or pound the metal and it stays together, it doesn't fall apart. Where you see the term ductile, we are essentially taking the metal and we're pulling it into a wire. Notice where you see high luster or shiny, it essentially reflects light. And notice that metals, they're very good at losing electrons. So we'll eventually talk about losing electrons with ions. Now notice that metalloids are in between. They are the least amount. They share properties with both. So they're kind of in between. And then if we look at the nonmetals, they're the second most amount of elements, and notice they're poor conductors. So they do not transfer heat or electricity. And we tend to use them in things like areas where we don't want to conduct electricity or heat. I'm sorry, I'm not thinking of anything on the top of my head, but definitely they're good at not transferring heat or electricity. Now, where you see brittle, that means they break easily. They don't hang together like the metals do. They are not ductile, so you cannot pull them into a wire. And notice that they are dull. They do not reflect light. And they tend to gain electrons, and we'll talk more about that when we form ions. So if you look at the left-hand side there, we have a bunch of metals. As an example, in the middle we have a group of metalloids, and then on the very right we have nonmetals. Now looking at this periodic table, notice that most of the periodic table is metals. Now, I don't like this step stair that they drew, okay? I want you to draw a line between boron and aluminum, and then you're going to zigzag in between. And notice it stops around polonium. Now, I would argue that there are, I would call astatine a metalloid along with all the other ones. Now, notice that aluminum is a metal, okay? You got to be careful because sometimes people forget, even though it's touching the step stair, it is not a metalloid, okay? And notice that anything is to the right of the step stair is essentially nonmetals. Okay, so here we have groups and families. You might notice that on some periodic tables they use Roman numerals. For instance, I've seen, and with your activity that you did the other day there was Roman numeral 1A and then Roman numeral 2A. I tend to use the numbers 1 through 18. So notice that groups and families, they tend to have the number 118. And then periods are 1 through 7, okay? All right. Now, this kind of highlights what you were doing with your trend graphing activity. And notice that in the bottom corner here, that's where the largest atoms are. And sometimes students have a hard time understanding this, but as we're going left to right, oops, let me try a different color here. As we're going left to right, the atomic number is increasing. And also, electrons are increasing. So because they're both increasing at the same rate, the atom actually gets smaller due to attraction. So the positive and negative signs cause the atom to get smaller. And that's only going left to right. When you're going down a group, it's a little bit different. You are adding energy shells. And because you're adding energy shells, the electron is getting further and further apart. So the outer electrons are less attracted to the nucleus. Okay. Here are some examples of atomic radius, and that's pretty close to what you were seeing with your graphing. And the reason why there are unknown sizes is these are human-made elements that they don't hang around long enough for us to tell how big they are. Okay, electronegativity. This is something that is actually based on the attraction of electrons with the nucleus. And it's similar to atomic radii. So it's the same reason. So you would argue that the greatest or largest electronegativity is fluorine, and it has obviously an equal number of protons and electrons, and they are tightly bound to that nucleus because of the attraction that they have with each other. Whereas if you're going down a group, you're adding energy shells, and as a result of it, the electron is getting further away from the nucleus, and it's not as attracted to the nucleus. Okay, ionization energy is the ability to remove an electron, and it kind of is similar to electronegativity. So we would argue that the interesting thing is helium doesn't have an electronegativity, and we'll talk more about why, but helium is actually the highest. And when we talk about where the electron resides, it'll make more sense with time. But the further away you get from the nucleus, the easier it is to remove an electron. So going down a group, the ionization energy is going to decrease. Whereas if you're going left to right, energy increases. Okay, so here is a summary of the trends that we were looking at with your graphing activity. And we'll talk more in class why reactivity is happening on the edges of the periodic table.